Hello, this is video B, and I'm trying a different lighting. I've got my back door open, so you will hear occasional cars. I live on Leestown Road, but hey, all of this is experiment, and we'll see how well these experiments work. And this is all stuff you know anyway. This is a review of some of the greatest hits, I suppose, of CS1 that I think we can summarize in 2 pictures. Some of the concepts that we need to know if we're going to get serious about understanding what's going on with the programming. One of these is a bunch of boxes. That box is in the middle. I'm going to try one more time to find a marker that makes a nice bold line, maybe in purple. Inside this box, I'm going to have 2 sub-boxes. One of them is the CPU. Oh, by the way, this is computer hardware. CS1 stuff. Sorry if I'm insulting your intelligence, but you'll get over it. We'll get to new stuff soon. This CPU is in the big box together with memory, also known as main memory. And I put those together in a box because those are what we in the biz might call tightly coupled. The CPU can see any piece of memory at once immediately without having to go through a bunch of rigmarole or even go through wires or anything. Those are right there on the same circuit board. Outside of the big box is a box called long-term storage. Ah, yes, it all comes back to you. The CPU is the thinking part of the computer. What it's doing is doing all sorts of mathematical calculations and comparisons and all that sort of stuff based on what is currently held in memory. So if the CPU is going to use it, it's got to be in memory. But it can't be in memory all the time because the contents of memory, you'll recall, or maybe it's brand new, you don't recall, but the contents of memory will disappear when you pull the plug, when the battery goes off, when you turn your computer off, when you shut it down. So how is anything going to be in memory for the CPU to use? That's where long-term storage comes in. Long-term storage, when you click on an icon on your desktop, you are actually telling the computer to load a program from long-term storage into memory, perhaps with a lot of saved data or whatever else might be needed to run that program. But that stuff is copied out of long-term storage into memory so that the CPU can see it and run the program and use that data and remember your high score from last time. Now, if you want to save it, oh no, look, I got a brand new high score, I don't want to lose it. Well, before the power goes down then, you'll need to save whatever state of the program is that you're running. You'll need to save that out to long-term storage. Now, maybe intermittently, you'll be playing video games while you're working on your stuff for this class this semester. But how this applies directly to us is when we are typing in our programs and running them and all that stuff, those programs exist in memory. If we got a version of a program that we spend a lot of time on and we were willing to keep that, we'll need to click on the diskette icon or whatever it takes to save it from memory out to long-term storage. So it will still be there when we power up the computer tomorrow and want to work on the program again. We can load it back into memory and get the CPU to do its operations on it. How do we get the CPU to do its operations on it? Well, we have to tell it what we want it to do, and that's where this box is coming from over here to the left, stage left, input. Input is just any device that is sending bits and bytes, zeros and ones, into the computer from outside the computer. Now, the easy ones are, let's see, the microphone that I couldn't get to work. That is not a good example of an input device. The built-in microphone on my MacBook that I'm using now, that's an input device I'm using. The iPad that I'm looking at is serving as an input device because I'm using its camera, and that is loading data into the computer that's going through a program and ideally changing it into a video that I'll be able to upload. That remains to be seen, the way things have been going so far. But an input device provides data to the computer. For our own selfish purposes, this is going to be the keyboard. We're typing in our programs in C++. They go into the computer, they're temporarily in memory in what's called a buffer. It's just a memory area that collects data until we do something with it. So here you go, you can type and type and type on your input keyboard over here. It puts the computer program in memory, and you're done for the day, you're going to save it and come back work on it tomorrow, then you will save it from memory out to long-term storage. Tomorrow comes back into long-term storage. How do we know if the program runs? Well, we run it and we look at our output device. Aha. The final piece to the puzzle. Moving around on a wiggly whiteboard. That says output, believe it or not. Let me hold it steady. Output. There. That looks more like output. An output device in general is a device that is designed to receive data, a flow of zeros and ones from the CPU in the main part of the computer here. The output devices are things like the screen that you might be watching right now. Oh, unless you're just listening to the audio, in which case a speaker is an output device. For our purposes, again, we're typing in on the keyboard. We'll be looking at very carefully what's going on the screen. That's where the output from our program will show up. If we use statements to print things on the screen, if you've got a program typed in and you want to take a closer look at it and mark it up and do proofreading and all that stuff, then you can send that to a printer. A printer is another example of an output device. So these are all very abstract in the sense that there are a lot of different specific devices that could fill in the blank for these boxes in the diagram. There's not a lot of choices for us, for the CPU. You've either got a Mac or a PC or some variation of those. And the memory, we don't look at that directly. There's all kinds of long-term storage. That could be a flash drive that's plugged into your computer. In the olden days, we had tape drives and diskettes and all that sort of stuff. The hard drive, even though the hard drive might be in the same box as your CPU and memory, it's still considered to be long-term storage. Why? Why is it different if it's in the same box as all this? Well, the distinction between computer memory and long-term storage is memory is the volatile stuff, the stuff that disappears when the power goes off, that the CPU can see without having to do anything special. For the CPU to be able to see a program that's stored out here in long-term storage, even though it's on the hard drive inside your box, or maybe it's inside flash memory. Maybe flash memory is the implementation of long-term storage on your computer. But the long-term storage, by definition, is the stuff that is not directly visible by the CPU until it's loaded into memory. Also, more importantly, perhaps, it does not disappear, thank goodness, when the power goes off. Otherwise, we would have no way to save anything for future use. You know, old habits kick in. This is the third or fourth time already I've had the urge to say it. I'll just go ahead and spit it out. Any questions? If there are questions, then get this diagram in your notes and write your questions off to the side, and that's what our Zoom sessions at each of our little mini weeks are for. That's what the Zoom session on Tuesday is for. That's what the Zoom session on Friday is for, to clear up any misunderstandings or confusion about the notes, and also to talk about upcoming projects and labs and so forth. Yada, yada, yada. I think I said a lot more about this in CS1 way back in the day. I am just as eager as you are to get past the point of saying, you'll remember from CS1, but hey, sorry, we're not there yet. That's computer hardware. Let's look at computer. Wait for it. There it is. Computer software. Hardware are actual physical things that you could touch. They might be tiny. I mean, the CPU might be small. You might touch it with tweezers or something. Computer software, that's like the thoughts in the mind of your computer, where the computer is your physical brain. Your thoughts would be your own personal analog software, meat-based software. The computer software are the actual programs, the electrons and so forth flowing through as your programs are running. So here's some terms for that. Program. One moment, please. Yeah, some people take their mufflers off around here. I guess that's cool. A program is a sequence of computer instructions. Emphasis on the sequence. In other words, it's going to go in lockstep, one after the other. Maybe occasionally we have an if to skip some statements, or maybe we have a while loop or a for loop to execute some statements over and over, but still, all of the statements of a program are going to be executed one at a time in a very strict sequence. It's not the same thing as a sonnet that you read and digest and look at it back and forth and go up and down and all that stuff, and you go back and read your favorite lines over and over again, and it doesn't really matter as long as you get the gist of it. There is no gist of the program. It really is got to be very deliberate, one step at a time. A high-level language is another software term. High level in the sense that it is removed from the machine. What's removed from the machine? Well, in our case, C++. That's a high-level language. Python. That's a high-level language. Java. That's a high-level language, etc. If you haven't done a lot of computing, you might think of it this way. A high-level language is any language you've ever heard of. Fortran, Python, Perl, if you've heard of Perl, Ruby, if you've heard of Ruby, Swift, a brand new one by Apple. Those are all high-level languages. Those are vulgar accommodations to humans, non-computing beings out there that need to know languages. They have words in them that are English words so that humans can handle it, like while and for and if and all that sort of stuff. So this is actually the domain that we'll be working in. Very specifically, we'll be working in C++ for this course. That begs the question then, if it's not a high-level language, then what kind of language is it? Funny you should ask. Then it is a low-level language or machine language. What are some machine languages? I remember the good old 6502. That was the Apple IIe machine language. I'm nerdy enough and geeky enough that I remember that from the late 70s. There's also, good heavens, there's also the x86 language. That's what's still used in PCs. x86 just means it's the 86 series. There's the 4086 and the 40186, 40286, and all those different variations. There's MIPS. Maybe you've heard of MIPS, maybe you haven't. If you have a pay cable TV box on your TV, it's machine languages in MIPS. Now, another etc. There are others. What is the reason for the difference? What's the fundamental difference? All of these down here, these machine languages, those are the languages of the computer. It's nothing but zeros and ones. Everything the computer knows how to do has to be expressed to the computer in zeros and ones, or it's not going to know what it's supposed to do. So for our purposes, what we've got to do is we've got to write our high-level language so that when it is turned into, and yes, it does have to be, when it's turned into machine language, then it will do our bidding. The computer will do what we've told it to do, not using machine language directly, but using our high language statements that our people speak. Very close to English. Well, not very close, no. But certainly closer to English than a bunch of zeros and ones. Remember the miracle of computers and data and everything else. Everything is zeros and ones. Remember your Frozen 2 DVD that you watch every weekend, however often. That's got nothing on it but zeros and ones. Shiny places and dull places that were burned into metal in a plastic sandwich. That's nothing but zeros and ones. All the instructions the computer does are nothing but zeros and ones. It's just a miracle. It's just unbelievable. But, let's see here. If we speak this, we speak C++, and we're running on a PC, let's say, and the computer only, whoops. Yeah, okay, I'll go with PC. And our PC, it can only speak the 86 series machine language, then how do we get from here to here? I feel another picture coming on. I guess I don't have board space since I was not very efficient here. But let's just keep in mind, computer speaks machine language, we speak high-level language. Hold that thought while I start drawing another bunch of boxes up here. Here's a box. Program source code. It is the source. It is the starting point. And I'm going to see if I can find enough colors that work. This is in a high-level language. High-lev-lan, abbreviated. High-level language. That is going to be our C++ code that we type in using an editor. We could type it in using Notepad or a word processor or something like that, but a Notepad, for example, that doesn't know the rules of C++, so it's not going to be able to help us automatically find errors and all that kind of good stuff. Another color. This is going to be a multicolor picture. Hang on. That's in a high-level language, and we type it in using an editor. E-D-I-T-O-R. Like an editor of a newspaper, except an editor for a computer language, it is like a word processor, but it's a smart word processor in that it does know the syntax or the language construction rules of some high-level language, so that when we type in something, it's almost like it's got automatic built-in spell check and stuff. But it even goes beyond that. It recognizes different tokens or different kinds of things that could happen in a language, and often, usually now, will make those different colors. This, I'm afraid, might be one of those parts in the video where if it doesn't make any sense, then another couple of videos, you come back and watch this, then you can smile and nod knowingly, ah, yes, that's what he was talking about. The editor does know the rules of the source code, otherwise we've chosen a bad editor for our project. And as we're typing it in, remember this is going into memory, we type all this in, it goes into a buffer in memory, and then we're going to need to save that out to long-term storage so that we can do things with it like, here we go, translate it into machine language. From program source code, it goes to, all of these could have program as a prefix to it, but I'm going to leave that off. These are all the same program, just different versions. This is the object code. The object code, switching to pink. I don't know why I even close these markers. I should just leave them all open. Get down there. Okay, this is in machine language. M-A, spell it correctly. M-A-C-H-I-N-E, LAN. All zeros and ones. So just like that, we've gone from stuff that we typed in that makes sense to us, ideally, in C++, with using an editor and another green. Here comes another green program. This arrow, to get along that arrow, we have to run it through a compiler. C-O-M-P-I-L-E-R. And yes, we will be doing this stuff. We'll be typing in C++ programs, we're using an editor, we'll run it through a compiler, and voila, as if by magic, it's object code that the computer understands that we no longer have any prayer of understanding, because it's all zeros and ones. Now, you might think, we're good to go. No, we're not. From object code, it's got to be translated into executable code. Executable code is what the computer actually runs. It is in the same machine language as the object code. It's all the zeros and ones. And before I resolve the mystery, let me put another green program up here to get from object code to executable code. It's run through a system program called a linker. All of these little green boxes with names that are smaller font, perhaps harder to read, all of the green boxes are system programs, meaning they are assistants, they are helpers. They are not things that we sit around and run in themselves like we might run a video game. I don't know anyone that's going to just sit there and run the linker for the heck of it. What the linker does, it performs this service of changing the object code into the executable code, and now I will answer the question that's in your mind that I never explicitly said. What's missing? Why isn't the object code executable code? Well, the linker actually puts together different object code files, different machine code files, into one big bundle called the executable code. What's missing over here is the library, L-I-B-R-A-R-Y. And I can read your minds, even through cyberspace like this. You're thinking, this is a programming class. We don't need no stinking library. That's not true. That's not true. Let me get my finger so you can see it. A library in our context here of C++ programming are pre-written programs that do ridiculously technical stuff that we don't have to write ourselves. What is something ridiculously technical? Something like, oh, I don't know, reading a keystroke from the keyboard. Someone just typed a capital A. That is ridiculously difficult to figure out in the computer. That someone hit that key and that's supposed to be a capital A represented in zeros and ones and all that sort of stuff. And it's supposed to go into our program. Oh my goodness, if we had to write a keyboard recognition understanding program to be able to write anything whatsoever in C++, we would all join together and run to the hills screaming. We would not write any C++ code. So the library makes things that happen very, very commonly or regularly in our programs and has that all pre-written by the nice folks at Microsoft or Apple, depending on whatever system we're running. That's why they get paid the big bucks. They write all of these separate programs that go into a library so that we don't have to. Aren't those nice people? They might even be worth what they get paid. Who knows? But the library, I should put the linker right here. You know what? I'm going to do that. The linker is going to move, Linker, to make it a little clearer what's actually being linked. What's being linked is the stuff that we wrote that is specific to our application. I want to know my average in the class. I don't care about all that other stuff other people are working on. But we will probably want to read stuff from the keyboard. That's one thing the library has to provide. We probably want to print stuff on the screen so we can see it. That's another thing that the library provides. We're just going to be using library programs, library routines all over the place. So yeah, this is an essential step, the linker. Now it's ready to roll. You know what? You're just not going to believe anything I say anymore. No. It's not ready to roll. All of this, everything above this, that's a dark green line. You can't tell. All of this is in long-term storage, LTS for short. If your program's going to run it, you remember from the previous picture that I had to erase to make room for this one. If the computer program's going to run it, it's got to be copied from long-term storage into, drum roll, actual memory. This, I put down the green too soon. This is long-term storage above the green line. This is memory, also known as main memory, below the dark green line. When it gets copied in here, sort of a legacy term, it's called the core image. I'll put core in parentheses. Core is the legacy term. That's when computer memory was a bunch of little, tiny little iron rings called cores. Core image. Image is almost poetic. That's almost a poetic name for your program. The executable code means it is possible to run now. It's complete. It doesn't have any missing pieces. The linker made sure of that. It tied together all of the library stuff we needed in the object code into an executable code file, but it's still a file sitting out there on disk or on our flash drive or wherever it may be. Maybe in the cloud. The cloud is another example of long-term storage. If we want to run it, we click on the icon or whatever it takes and pull a copy, also known as an image. It's not trashing what's out here in long-term storage, just making a copy of it, almost like a reflection. I told you it was poetic. The image term is poetic. It's like a reflection of what your executable code looks like out there in long-term storage. Why do we need to make a copy? Well, only things below the line in memory are things that the CPU can actually see and operate on. Only things above the line are things that are going to still be here tomorrow after we turn the computer off and turn it back on. So both of these are essential. How do we get there? I didn't leave room, but we need one more green program, the loader, L-O-A-D-E-R. All these little elf helper programs that, well, I don't know why I put that on the green line. There. It's got its own separate green box. The loader. You execute the loader when you click on a desktop icon. You are telling the loader, find the associated executable code out on my hard drive and copy that into memory and start running it. And that's exactly what the loader does. It makes a copy of the executable code associated with that icon on your desktop, makes a copy of that in memory, and then tells the CPU, here it is, ready to go, and tells it the address and memory of the first instruction of your program. What could be simpler? Oh dear, probably a lot of things. But these are all, like I said, are pretty abstract. Oh, I left out the pink, didn't I? Even though my marker's still open. You know what? I could draw a dividing line right here. I'll do a dotted pink dividing line. There. This is high-level language, close to English with English words in it. Everything below the dotted line, all this stuff, that's all machine language. It's all zeros and ones beyond that point. So the only one of these that we have any prayer of actually trying to read would be our actual source code. Why do we need to know these pieces? Every time you run a program, it has to go through this complete life cycle. You type it in here, and we run it through the compiler, make it object code. Then we've got to link it, make it executable code. Then it's got to be copied into memory as a core image, and then we run it. Oh no, we got the wrong answer. It said my average in the course is -17, and there wasn't even a way to make a negative grade. Back to the drawing board. We don't go backwards through the life cycle, we've got to go clear to the top. If you've got an error, you've got to change the source code, save it to long-term storage, then run it through the compiler, do all this stuff again. I tried to slow down a little bit on that. Maybe that was undetectable. The reason is one of the top 5 logic errors, one of the top 5 mistakes you make when you first start writing a compiled language set of programs could easily be, I changed my source code, but I still get the wrong answer. It still gets -17 for my answer, and you have no idea how impressed I am with myself right now for remembering that I said -17 before. That'll never happen again. -17, that's not the right answer, and I changed it so that it should be correct now. You can't just change it here and expect this to be different, because none of these others will be different. You change it, you save it, and then you've got to run it through all this pipeline again, go through all those steps. Otherwise, even though you went to all the trouble of editing it, otherwise, if you just edit it and then run it again, you're running the old core image. You're running your old executable code from the last time you did deliberately go through all of the multicolor steps in purple and green and pink. Got it? I'll remind you of that. My guess is, I'm going to go out on a limb and say that I'm going to have to remind, don't feel bad if you're this person, I'm going to have to remind at least one person at least once this summer school session that, yeah, even though you changed it, you got to do all this other stuff. Otherwise, you're not going to see any difference in behavior. I feel like I'm ending on an insulting note. Maybe this entire summary of old stuff, good heavens, is an insult to your intelligence, and I apologize for that. I appreciate your indulging me and dragging you through all that. But I'm going to leave CS1 behind us, and we're going to do nothing but look at brand new CS2 stuff starting with the next video. But until then, I'll see you online.